contraction and time dilation are two very important consequences of the special theory of relativity. So what really happens is that when an object is moving relative to some inertial frame of reference placed at rest, so what will happen that the length of the object is contracted and the time for the object is dilated. But since we cannot really define an inertial frame of reference placed at rest, according to Einstein's principle of relativity, any two inertial frames in this universe we can say that both whatever we are observing, whether that is length contraction and time dilation, the values of length and time and everything, they should be treated equally in both the inertial frames of reference. So if I'm saying that A is moving relative to B, so that is equal to saying that B is moving relative to A in just the opposite direction. So is it the length of A that is being contracted, or is it the length of B that is being contracted? And the same holds for time dilation. So I was just confused in this thing.
It's a really, really good question, Sarif, and it's something a lot of people get confused by. The answer is both things happen. So say there's a train coming towards me and I'm on another train. Because of how fast that train is traveling, there's length contraction, right?
Yes,
because it's moving at relativistic speed. I see that length contraction. Now let's imagine that you are on the other train and you look at me. You don't see the length contraction of your own train because you're at rest with respect to it. But what you see is you see the length contraction of my train. So in some sense, special relativity is completely symmetric in that way. It depends on which observer. So both things are happening, but they are happening according to a measuring stick that each observer will make. And the same thing is with time dilation. Time dilation is just sort of the sort of time aspect of length contraction.
Oh, so in whichever reference frame we are acting according to that reference frame, and whatever we are observing is according to that special reference frame, right? Yes,
that's right. Yeah. So whatever reference frame we're in makes a difference.
Yeah, and then so what I would like to ask is about gravitational waves and the no-hair conjecture. That I was finding that these two results are like seeming quite contradictory. Like so gravitational waves, when there are two black holes and those two black holes come to collide each other, so they will form kind of ripples in the curvature of space-time. That is, they will form gravitational waves. So, and I also read it somewhere and about the no-hair conjecture, that we can never gain the information about the star or the black holes that formed a specific kind of black hole. Like we can never gain the information about the star that is forming a black hole, whether that star was in the complete spherical shape or a cylindrical shape or any other kind of shape, whether it had magnetic field lines. But sir, then if the same holds true for a black hole that is being formed